Dark matter represents one of the biggest blanks in our current understanding of the universe. It's a term used to refer to the estimated 83% of the mass in the universe that we currently can't identify. So how do we know that this mass exists? Through gravity. Let's start with a quick refresher about orbits. What does it mean for an object to orbit something? Well, say an object is traveling past a much more massive object, like an asteroid passing the Earth. The Earth's gravity will accelerate the asteroid, bending its path. For an asteroid at a given distance from the Earth, there's three possible outcomes to this, depending on the asteroid's speed. If it's going fast enough, then its trajectory will be altered, but it will eventually escape the Earth's pull and continue on its way. If it's moving too slowly, then its path will be curved sharply enough to send it crashing down into the Earth. At the perfect speed, the curvature of its path will keep it moving around the Earth for good. It will then be in orbit. These same principles apply on the scale of stars orbiting the centers of mass of their galaxies. Since these stars are in orbit, we expect them to be traveling at a particular speed given their distance from galactic center. In 1932, the astronomer Jan Oort discovered that stars in our own galaxy were moving faster than we'd expect. Based on our estimates of the mass of the Milky Way, these stars should have been going fast enough to fly free. We would expect that the speed of orbiting stars in our galaxy should decrease as we get farther from the bulk of the galaxy's mass. But in reality, the speed of stars stays pretty constant for a long way from the center. He reasoned that our estimates must be too low, and there must be more mass in the galaxy than we can observe. This mass must be spread throughout and beyond the visible portions of the galaxy. Whatever this mass was, it wasn't emitting light or other forms of electromagnetic radiation. That's what we use as our main way of observing the universe. If something isn't emitting or blocking electromagnetic radiation, then our telescopes are powerless to observe it. So this mystery mass became known as dark matter, and the region it occupies around the visible galaxy is called the dark matter halo. Further evidence for the existence of this unknown mass was found by Fritz Zwicky in 1933, on an even larger scale in the orbital velocities of galaxies and clusters. He found that the movements of the galaxies also belied invisible sources of extra mass. Modern techniques using the effects of gravity on light have even been able to map out the distribution of dark matter in the universe. Let's take a moment to explore that. Einstein's theory of general relativity predicted that gravity is a bending of space-time, and so it should bend the paths of light as well as objects. Of course, light moves very fast, so this bending has to be observed over huge distances. This bending of light was confirmed during a solar eclipse in 1919, when the moon blocked the sun and allowed us to see stars that were very, very close to the sun's edge. These stars, it turned out, were at slightly different locations than they were supposed to be. What was happening is that the light coming from them was being bent around the sun and arriving at Earth from a slightly different angle, causing their images to appear at a different location in the sky. This phenomenon is called gravitational lensing, because gravity is acting like a lens to bend the light. At large scales, massive galaxies can magnify and distort our view of the galaxies behind them. This is called strong gravitational lensing. It can result in smeared or even doubled images. When there's less mass in the way, distant galaxies appear slightly sheared. This is known as weak gravitational lensing. By looking at many galaxies, we can statistically recover the amount of shear in a given part of the sky, and thus measure the amount of mass between us and the galaxies we're looking at. Maps of matter developed with this technique have shown that much of the matter we find can't be accounted for by observable objects. So most of the mass causing this weak gravitational lensing, this shearing of the visible galaxies, is actually dark matter. Recent efforts to model the early universe have shown that the mass provided by dark matter was crucial for the development of galaxies after the Big Bang by helping to pull matter together into clusters. One explanation for dark matter might simply be massive objects composed of normal matter which don't emit electromagnetic radiation. These could be anything from black holes to orphan planets that have left the orbit of their star. Such objects are known as machos, massive astrophysical compact halo objects, because they're found in the dark matter halo. The key prediction here is that if dark matter is a bunch of machos, its mass should be in clumps. Although these clumpy objects wouldn't emit electromagnetic radiation, their density would cause some gravitational lensing that we could then use to detect them when they pass between the Earth and a distant star. Since machos are actually relatively small in the cosmic sense, their lensing effect wouldn't double or even smear the image of a distant star. Instead, they bend the light very slightly so that some of it which would have otherwise missed the Earth gets directed back towards it. This ends up making more starlight visible from Earth, so although the shape of the star is not really affected, it does appear to brighten transiently. This counterintuitive effect is known as gravitational microlensing. Research efforts watching for these brightening events have found far fewer than we'd expect if dark matter was entirely composed of machos, so it's believed that machos can only account for a small fraction of the missing dark mass. Another idea is that dark matter might represent a new type of particle entirely. This particle wouldn't interact much with regular matter or electromagnetic radiation, so we wouldn't be able to observe it with our telescopes. It turns out that we already know of a particle with these qualities, the neutrino. Neutrinos are weakly interacting particles with very small mass that travel at near the speed of light. During the 80s, it was thought that perhaps dark matter was composed of tons and tons of neutrinos. However, efforts to model the early universe with neutrinos as dark matter have shown that the neutrinos wouldn't really help matter pull together into galaxies. A more massive, slower moving, and thus clumping friendly particle would be needed to do this. This hypothetical new particle is therefore known as a WIMP, a weakly interacting, massive particle. Many research efforts to detect WIMPs are currently underway. The question of dark matter is one of the most exciting issues in science today. We're talking about the nature of the majority of the universe. Everything we've ever discovered, all of reality as we currently know it, is only a small subset of what exists. This is a mystery that will only be solved by studying the universe at both the largest and the smallest of scales, as astronomers and particle physicists come together to advance our understanding of the world around us. Thanks for watching Explaincast. If you liked it, please rate and subscribe, and feel free to send me suggestions for future episodes at twitter.com/explaincast.